going to get it if I leave it here all weekend.
Okay, maybe
You
thought it was
Right.
You know, I meant
Spirit.
a
Maybe
piece
thought
of
it was
paper.
David.
Spirit.
David would get it.
Look at it.
Anyways,
Maybe
okay.
it's still
So,
down.
here's what we're going to start. I had kind of a discussion with myself prior to copying this for you. And I felt like I could just do this probably a little bit easier without using the note handouts, but I think you guys have come to like the fact that it's all spelled out. However, please notice the time check. And also, I'm going to try to give you a big overview today first, before we get into the specifics. And you'll notice that the last page in the handout, last side of it is blank. So will you turn to that last blank side, please, for me? I'd like to try to start with just kind of the basics. Now, when we start this, let me give you a little heads up. You're going to think to yourself, why in the world would I ever need to find, and you'll notice over here, I've sort of outlined this next little chapter for us. Why would I need to find the area under a function or under a curve? So when you get to your next test, and then you realize you just finished yours and turned it in now, it's going to be a rather short chapter. First thing to know is that since optimization didn't fall on your last test, I haven't done this one, but we'll review it before the test. And then all these other things here, which some of these might not make any sense to you just yet, and that's okay, have to do with finding the area under a curve. When I say curve, I need you to understand that it might be a straight line, it might actually be curvy, right? And then you might think to yourself, how are you supposed to find the area under something that's curvy? That's exactly where the calculus developers were coming from. How do you do that? So we're going to start today with something that's not curvy, and I'll show you kind of how we head into that. We'll see how far we get. So the idea is really for the rest of this, finding the area under a curve. There's probably one more thing I need to put up here. But notice that the calculus part of this doesn't show up until the very end. So what we're going to stick with today are some geometric things, all right? So on the page that you have, on the very back page, there's blank, and I'm asking you to pick the blank page for me. What I'd like for you to draw would be a relatively small graph over on the top left side of the back page. First quadrant is totally fine. And what I'd like you to do is label this function. Understand that it's going to be f of x equals 6. And you're going to notice I'm not going to put all the hash marks on the y-axis. That's going to be pretty consistent with the ones that we do on the back side. I didn't give the graph paper for it. We're just doing the big picture kind of idea. Now, if I asked you guys to describe to me what kind of shape that is, if you were to sketch it, my hope is that you do not need a graphing calculator to be able to sketch that. Am I correct? Okay, good. Tell me what kind of shape that has. Straight line. I love when people say straight line. Yes, exactly right. And tell me how that line is oriented. Straight, yeah. How? Is it an increasing function, a decreasing function, or something different? Something different. Which way does it go?
I was already wrong the first time.
Horizontal.
Horizontally. 6 looks like that. Are we good there?
Yeah.
So it's nice horizontal line. Now let me add a little bit of directions to this. Our job today is to find the area under the function, so I'll put under f of x, between x equals 1 and x equals 4. And then this is going to be implied. The more that we do, you'll be okay with this. And then it may change after we get into this a little bit, and above the x-axis. Now, there are places and times when sketching is going to be important. And you're going to notice if you looked at the front page of your graph that I actually do have a lot of sketches drawn for you already. And that's going to be important. Whether you get that way, the test questions that way on the actual AP test is a different story. But for right now, you're just learning it. We're starting out from scratch. So we've got this function, and we've got the directions. Find the area under the function between these x's, between 1 and 4. So what I want you to do on your x-axis is go ahead and label 1 and 4. So put those on there for me. And it said finding the area underneath the function, so obviously it's underneath this horizontal line. And these x's are like telling you where to start and stop finding the area. So what I want you to do is use a straight line and draw up to your function. So this line would go through x equals 1 all the way up to 6, and then x equals 4 all the way up to 6. And I want you to use your magic geometry powers and go, I know what shape that is, because here's the idea. We're trying to find the area of that. I'm trying to stick with things you know how to do without any calculus just yet. What kind of shape do you see there? rectangle. It's not a square. It might look like a square based on how I drew it. But look at your dimensions. Okay, so would you guys agree that the area of a rectangle is what times what? Base times height, or you guys could call it length times width. It really doesn't make any difference either way we do it, right? So how wide is this segment right down here? 3 units wide. So one of the dimensions is 3 units wide, whether you want to call that the base or the width, it doesn't matter. And then how tall is this rectangle? 6 units. So would we all agree that we get an 18? Okay, so that's your first example in the concept of what we're starting into. Finding the area underneath a function. Let me say it that way. And when I use the phrase finding the area under a curve, I use the word curve loosely because this one obviously didn't actually curve. Okay, to the right of that, or you could put it below that, doesn't matter where. What I'd like for you to do here, for this f of x, is go ahead for me and we're going to sketch the line f of x equals 2x. Okay, so a new example. This is, again, on the back page. Here's example 1 and here's example 2. These are the only two I'm going to do on the back page for you to give you a bird's eye view and kind of an intro to it. And then we'll take a look at what we do when things actually curve. So this one, obviously, what kind of thing is this? Your answer to the first question would probably be apparent, or probably correct. A straight line. And tell me more about the orientation of this. It increases, beautiful, thank you, good calculus interpretation there. Where does it go through your y-axis? 0. Now you're going to notice we're not putting any y values on here. Are we okay with just drawing a line that does something like that? And obviously our line goes on forever and ever and ever. Same with this line up here, but we didn't use the line going on forever and ever and ever because we were told to start and stop at x equals 1 and 4. So for this one, I'm going to ask you guys to do this. Find the area under the function. I'm going to not write above the x-axis because that at this point is implied. It's always going to be above the x-axis until we describe things differently. And I'm going to put between x equals 3 and x equals 12. Okay? Now once again, no graph paper here because we're not going to need it. We're going to be able to do the computations together and not have to worry about it too much. So when you do these problems, in the near future, probably by about Tuesday, this whole sentence, all the sentence structure over here, is going to be written in calculus notation. Right now I'm writing it out for you. Okay, but there's a short, quick notation because you all know mathematicians like to have very succinct notation that says a lot, explains a lot, by not writing a lot. So the idea of every time we do this is you've got a function given. You're going to find the area between that function and the x-axis, and it's going to need to tell you where to start and stop for your x values. So will you do this for me? Over here on the left side, since we don't have anything written down, just go ahead and put 3, because it says start at 3. We're finding the area, again, between 3 and 12. And then over on the right side, however far you think you need to go, I am going to go ahead and draw the function so that it goes beyond that. We realize we're only interested in just this area inside here. Now that shape, not a rectangle, right? Not a rectangle, is it? Now, we can do this one of 2 ways. I'm going to erase my orange for just a second. You're about to see that we're going to follow a Greek mathematician named Archimedes, who decided whenever we're trying to find areas we're not sure how to do, we're going to cut them into pieces. So one thing we could do here would be to just go like this. If we took this section and kind of split it into 2 areas, we can find the area of these two geometric shapes. Because you guys know how to find the area of this, right? What's this shape? Rectangle. And this shape up here?
Quadrilateral.
You know what it is. Okay. Or, what's the big shape here? What would it have been? What's the big shape? Trapezoid. If you remember the trapezoid formula for area, great. Not everybody does it initially, which is fine. So let's maybe just go with this. Are we okay with that idea so far? Okay, so let's do this. First of all, my question is going to be how wide is the base of this, both rectangle and triangle, right?
Yes.
Yeah.
Good. Glad you agree. How wide is that, ladies and gentlemen? It's 9 units wide. Nicely done. Beautiful work. And how tall is it from 3 to this point on the curve? Well, this is where our function is going to come into play. How'd you get that? Beautiful. Plug it into your function and you find out that y value is 6. I'll just put 6 right next to the point so that you guys know my graph is obviously not quite drawn to scale, but area 2 down here. And let me kind of do this with area 1 and area 2 and sort of circle them. Area 2 then would be found by doing 6 times 9. Would you agree with that? Bless you. Again. Area 2 is found by doing 6 times 9, 54. Now, area 1 is found by doing the area of a triangle. Agreed? So we have to be a little bit careful here. If we said, how tall is this? What we want to do is find the top, bless you again. We want to find the y value up at the top. That may not be exactly the height of the triangle. Agreed? They're quiet. How big is that y value point right up there? Well, how'd you guys get 6?
4.
3, type in 12, you said it's 24? I would agree with that. Now, does that mean your triangle is 24 units tall?
No.
No, it doesn't. How tall is it?
18.
24 minus the 6, so it would be 18 units tall. So how do you find the area of your triangle? Nice. 1/2 base times height, so it's 1/2 times 9 times 18. How are we doing there? Okay. Now, you probably don't need a calculator for this. If you realize you have a little bit of canceling, the 2 goes into the 18, and you're left with 9. Big sigh. Goodness. So we're left with, I think, 81 plus 54. Anybody have a calculator out? You can do it in your head. Come up with an answer.
I got this.
I figured you might not need a calculator. How about 135? You can check it and make sure that I'm not just messing with you.
I did that in my head when I got
Beautiful. Beautiful, beautiful. Okay. Now, here's the thing. Not every function that we work with in calculus is going to be nice and straight like these, right? You can clearly, you know that the majority of the functions you've worked with in Algebra 2, and in pre-calc, and even in calculus so far, curve. We've looked at e to the x, we've looked at logs, we've looked at polynomial functions, all kinds of stuff. So the question became with the calculus mathematicians that were developing this along the lines, how do we find the area of something that curves? So go back to the front side of your little sheet. The front side of your sheet has example number 1, and it gives you, well, first of all, let's do this. It gives you the function 9 minus x squared. I'm going to erase the little number 1. Up at the top of your sheet it says we're going to work with 9 minus x squared. And the very first thing it says to you guys is sketch the graph to the right of the little description. What is 9 minus x squared? Is it a straight line? No, it's not a straight line. What kind of shape is it? A parabola. Good. And is this parabola going to be opening upwards or downwards? Downwards. And where's the y-axis intercept going to be? 9. Tell me why you know that. Yes. Tell me how you know.
The 9 first value.
Because if you plug in the 0, you get 9, right? Okay. If we look at where does it hit the, first of all, do we agree that it's symmetric? Yeah. Hopefully that you're looking at that picture seeing symmetry. Where does it hit the x-axis? Could you do that without doing any kind of algebra? Think about this. If you were to set this equal to 0, what number would 3 have to be? 5 was the question. What number would the x-axis have to be? Negative 3 and 3, right? Okay. So here's the next little statement. We're sketching the function. We just did that. Now if you look at number 2, it asks you guys, now let's consider the following. Let's just look at, if you look at my interval notation I've written, look at 0 to 3 on the graph. Well, 0 to 3 obviously is just this part over here. So we're looking at the graph underneath the function, starting at 0 and going over to 3. Now that should look not like a formula that you found in geometry. We don't have a formula for the area underneath a parabola or a quadratic function. So the mathematicians came up with, they devised a method that went like this. Well, we don't have a formula for it, so let's cut it into pieces. A little bit like this, but not as exact, because this is curvy. And so they came up with several different options. You'll notice in our list here. We've got, you're not going to understand this just you will in a minute. Left, right hand, rectangles, that little thing is for rectangles. Then this says midpoint, and that does say trapezoidal rule, but we'll get to that a little bit further into the future. Let's start with number 1. By the way, your pictures for 1, 2, 3, and 4 are all the same. I just drew them for you 4 times. Okay? I'm just taking this graph here, making it a teeny bit smaller. Just know that this is this shape. We're going to examine it 4 different ways. The first of which, first of all, let's do this. You already have this on your x-axis. You have the points 1, 2, and 3. Will you please draw me a vertical line all the way up to the function, up above 1 and above 2, we don't have to do that at 3 because that's your x-intercept. So will you do that for me? So we're trying to find the area underneath the curve. However, we can't do that because if we're only going to use rectangles, this shape areas 1, 2, and 3 are not rectangular areas, right? In fact, they're not. They look close to. What kind of shape do they look close to? Trapezoids, but they're not even trapezoids because the tops are curvy, right? Okay. So one of the options is, and you guys will notice, this one is spelled out for you on your sheets. It says left-hand endpoints are all abbreviated with LHE. It's pretty common. Left-hand endpoint. And here's what I mean by left-hand endpoint. What we're going to do is we're going to take area 1, and I'm going to refer to this as area 1 so that you know what I'm talking about. Area 2 and area 3. When I say left-hand endpoint, I want you to take a look at this.